Good morning. We are Group 57, also known as ML Dogs, and this is our SC4000 project presentation. Today, we'll start with the project overview, then walk through our data analysis and preparation. After that, we'll cover the models we built, our results, and our key findings before concluding. The challenge was ambitious: improve standard smartphone GPS accuracy from several meters down to the sub-meter level. We were given raw GNSS and motion sensor data from Android phones with the goal of building an algorithm for highly precise location tracking. The impact of this is enabling new applications like accurately detecting which lane a car is in. This required techniques like sensor fusion and outlier removal. Over 1,300 teams competed, creating a strong public benchmark for this research. Our success was measured by the distance error against the ground truth. Our first step was a deep dive into the data, known as exploratory data analysis or EDA. We found the data was highly heterogeneous, organized by different drives and phone models. A major initial hurdle was discovering multiple timestamp formats that all had to be perfectly converted and synchronized. Data quality was our biggest challenge. The GPS and motion sensors had a massive sampling mismatch. We also found significant data gaps and missing values. In short, the data set was sparse, noisy, and inconsistent. Our key takeaway was clear. The variable signal quality and missing data meant this problem could only be solved with extremely strong preprocessing. So that led us to our preprocessing phase. We built a pipeline to manage this. First, we standardized everything into a unified schema and normalized the timestamps. Then we extracted features from the raw GNSS signals, the GNSS status, and the IMU motion data. Critically, we also generated our own high-precision baseline using PPK processing. Finally, we fused all these new features, aligning them with a 50-millisecond window and adding rolling statistics. We used DAS to process this in parallel, resulting in a single featureized CSV file with non-coherent data. It was largely because our pipeline code was majorly created by Gen AI, which led to a lot of faulty logic. This led us to make a more systematic approach of using source codes and academic papers to our advantage. Now, before we could even think about machine learning, we had to solve a fundamental data problem. A standard smartphone's GPS is incredibly noisy, with errors often exceeding 10 meters due to atmospheric delays and clock drift. Our entire strategy was built on post-processing kinematics, or PPK. The key insight is that a nearby base station experiences the exact same atmospheric noise. We use an open source tool called RTKlib to take the data from our phone and the base station and essentially subtract this shared error. This cancels the noise and lets us use the hyper-precise carrier phase, or ADR, for positioning. To do this, we built a hybrid pipeline. We use Python to orchestrate the workflow, while the original C executables from RTKlib handle the high-speed computation. This pipeline had to automatically fetch two external datasets, satellite navigation files and the base station data. This is where we primarily hit our first wall. The download links for the nav files were broken, returning error 404s. So we had to reroute our script to a more reliable archive. Even worse, the base station data would sometimes fail to download silently. We had to build in explicit error handling to catch these failures before they corrupted our data. Our first attempts were a complete failure. The initial run failed to lock onto the precise carrier phase and was forced to use the noisy pseudo-range data. The result was catastrophic, with errors from 100 to 1,200 meters. Our final method was the breakthrough. By correcting our configuration, we successfully enabled differential cancellation. This eliminated those dangerous outliers. We had one last bug. Our comparison script kept failing because RTKlib's time format was incompatible with Unix timestamps, which we fixed with a robust parser. The results show the full story. The before plot on the left shows our initial 2.5 meter median error. After our PPK solution, we achieved a 1.24 median error. This new high fidelity baseline is what gave us our 3.004 Kaggle score. This was the most critical step of our project. We successfully transformed raw, unusable data into a high precision data set. This became the essential foundation for our machine learning model.